Pascal's triangle.
The numbers in each row of Pascal's triangle are binomial coefficients.
Did you know there are many hidden facts within Pascal's triangle? In the third column, there are triangular numbers. You can think of the triangular numbers as the number of dots it takes to make various sized triangles. Pascal's triangle is a triangle of numbers where each number is the sum of the two numbers above it added together. For example, 1 plus 1 equals 2, 1 plus 2 equals 3, 3 plus 3 equals 6, and so on. Pascal's triangle is used for binomial coefficients. The binomial theorem refers to the pattern of coefficients that appear when a binomial is multiplied by itself a certain number of times. Pascal's triangle can be used to determine the expanded pattern of coefficients. Alright, so our example problem is a plus b to the fourth power, and since it's to the fourth power, we will be using the fourth row of Pascal's triangle. We use the coefficients 1, 4, 6, 4, 1. Alright, we start with a, so we take it to the highest power, so it's a to the fourth. Then we go down, so it'd be a to the third, a to the second, a to the first, and a to the 0, which is also 1. And then you take b, and you put it next to a, and you start from the lowest power, so it's b to the 0, b to the first, b to the second, b to the third, and b to the fourth.
For our second example problem, we're going to be doing a plus b to the second power, which is equivalent to a plus b times a plus b. So since it's the second power, we're going to be using the second row of Pascal's triangle, and the coefficients in that row are 1, 2, and 1. And the way we can work out this equation is, since the first coefficient is 1, there's only one way to get to a squared, which is by doing a times a. And then there's two ways to get to ab, because you can do this a times this b, or this b times this a. And then there's only one way to get to b squared, because you have to do this b times this b. So therefore our answer to a plus b to the second power would be a squared plus ab plus b squared. In the real world, one way we can use Pascal's triangle is in its use with combinatoric questions and in particular combinations. For instance, when we have a group of a certain size, let's say 10, and we're looking to pick some number, say 4, we can use Pascal's triangle to find the number of ways we can pick unique groups of 4. In this case, it's 210. To bring in a real-life example, let's say our favorite pizza shop offers 10 toppings, and for a certain price, they'll put on 4. How many unique pizzas could we create? The answer would be 210.
In real life, Pascal's triangle can be used to determine how many different combinations of heads and tails you can get depending on how many times you toss the coin. Let's say you toss a coin 3 times. It lands heads, 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 tails, heads, tails, heads, tails, heads, 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 tails, 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 heads, tails, 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 heads, tails, tails, tails. There is one combination that will give you 3 heads, 3 combinations with 2 heads and 1 tail, 3 combinations with 2 tails and 1 head, and 1 combination that will give you 3 tails. This is the 1, 3, 3, 1 sequence in Pascal's triangle, which is the third row. In this situation, you could use Pascal's triangle to determine your odds of what the coin will flip.
One reason we chose Pascal's triangle was because the triangle figure looked very interesting and we wanted to learn how to apply it to our math.
The reason I chose Pascal's triangle was I was really interested in the way it worked. While researching Pascal's triangle, I found many sequences within the triangle. For example, the first 7 numbers in the Fibonacci sequence are also in Pascal's triangle. The triangle also reveals the base powers of 11. After working on Pascal's triangle, I feel like I've prepared myself for math class in the future.